All right, we have our last video, section 4, for our unit 10. We're going to look over algebraic transformations. Now, these are transformations done onto graphs of our equations. Equations or functions. So we will look first at parent functions. These are kind of our basic functions or the basic equations, and then we'll look into how they transform. So as a review, an x-intercept is just the coordinate where the graph crosses the horizontal or the x-axis. It's the x value when y equals 0. So you can plug in y equals 0, plug in 0 for y, and solve for whatever x is. That would be one of your x-intercepts. Same thing, the y-intercept, on that up and down, the vertical axis, the y-axis, it's just the y-coordinate when the graph crosses that spot. So you can plug in 0 for x, and whatever you get for y, that would be your y-intercept. Parent functions, then, are just the basic or the standard graph of a family of graphs. So families of graphs are the four things we're going to look over: quadratics, square root, absolute value, and cubic. So we are going to look at four different families of graphs, and then the parent function is the original or the basic one of each. So we're going to start first with quadratic. This is our parent function. Our parent quadratic function is just f of x, or you can call it y equals x squared. Now when you do y equals x squared, it makes this parabola, this kind of U shape. Now if we plug in like x is 1, well 1 squared is 1. You can see that right on the parabola. If we plug in 2 squared makes 4. Again, you can see that right on the parabola here, right on our graph. So when it's this basic, easy parent function, it should make this nice, perfect little U shape. Now, there are a couple different ways to write out a non-parent function of a quadratic. In standard form is what we call it. That's the ax squared plus bx plus c equals our y value, or the f of x. Again, this is just function notation. This is saying our y value, we're calling it function of x. Whatever y is depends on x. So we call it function of x, or f of x. So y equals ax squared plus bx plus c. We've looked at that before. That's our basic quadratic form. Now, there's another way to write that. You put it in this form. A times this amount, x minus h squared. So notice there is still a squared. Anytime there's a squared, that's what tips it off that this is a quadratic. After x minus h squared, you would add k. Now notice, a and a, this is actually going to be the exact same value. Whatever your a value was up here, it's the same a value here. Now there's something very cool about this vertex form, and we're going to get to that a little bit later. But we're going to go over x-intercepts here really quick. There can be 0, 1, or 2 of them. I'm going to show you how that works. If we had a parabola that looks something like this, so it makes that U shape, comes down and it touches right on the line, well, there would be one x-intercept. There's one time when it touches that line. If we brought it downwards like this, notice it touches twice, once here and once here. There are 2 x-intercepts. And let's say we brought it way up here. Notice it never actually touches this line, so there could be 0. So there can be 0, 1, or 2 of our x-intercepts. There don't always have to be 1. Now, no matter where you're at with this parabola, if this line continues forever and this line, because it's all one continuous line, you will at some point always cross the y-axis. You know, wherever you are sitting, or wherever this thing is at, it has to cross this y-axis somewhere. So you just plug in 0 for x and then solve for whatever y is. That's how you'd find it. And note, there has to always be exactly one of them. You can't have a quadratic function without a y-intercept. Now, very important reference points for these kind of equations or these kinds of graphs are the vertex. Now, the vertex is at hk. Notice, h right here and k right here. Inside of this, it says x minus h. So whatever x is subtracting, so let's say it was like x minus 3, you would know that your vertex is over here at 3. If it said plus k or plus 2, we would know our vertex was at 3 2. Right here would be our vertex, and everything would stem off of that. It would have to look something along those lines. Okay. Another way to find these h and k values. The x value, or h value, if we were given this form, is negative b over 2a. And we looked at that when we were graphing parabolas before. Once you know your x value, to find the y value, just plug in x back into this equation and solve for y. That would be how to find that extra vertex point. So your h and your k, and remember your a value is always the same right here. So that's why it's kind of special. It's kind of nice to have this vertex form. It tells you exactly where the vertex is, and this a does something as well. Now, how do we transform everything from this red parabola to, what if I drew something like this blue parabola with a vertex right here? How do we go from this one to this one? Well, each of these pieces, A, H, and K, has a certain characteristics or a certain trait about it. Each one does something special. A is called our stretch. If A is bigger than 1, then the parabola will narrow, or it grows. What it means is it's growing faster. So I'm going to use blue for this one. If we started at the same spot as before, so our vertex doesn't change, but instead of a value being 1, if a value was 2, so it is bigger than 1, instead of going over 1 and up 1, we'd be going over 1 and up 2. It's growing twice as fast. Instead of going over 2 and up 4, we'd be 2 up 8, twice as fast. So notice this would be getting a little bit narrower because it's going up faster. So if a is bigger than 1, the parabola will narrow, or it grows. If a is in between 0 and 1, then the parabola will get wider, or it shrinks in a sense. It's like it's growing slower. I'm going to do this one in green. Starts right here, and we have like a fraction, like 1/2. So it's only growing half as big. So not up to 1, it's up to 1/2. When we're over 2, we're not up to 4, we're only up to 2. So it's going to grow a little more slowly or wider. Okay, and that's if a is in between 0 and 1. Also, if a is negative, everything flips upside down. So I'm going to get rid of these ones, a couple of these, leave those extra dots. I'm going to draw this one in yellow. If we start at our vertex here, instead of swooping upwards, if a was negative, we would be swooping downwards, like this. Everything just kind of flips upside down. That's only if our a value is negative. But then still, if a value is negative and a fraction, so in between 0 and 1, that would still make it wider. If a value was negative, but it was still bigger than 1, so like -3, it would still be getting narrower. It's just going down now. Okay, so that's how a, this value in front, will affect that graph. I'm going to get rid of some of these now. And that last one. How does h affect the graph? Remember, h is this spot of the parabola. It's part of the vertex. It's our x value of our vertex. So if h is positive, which remember means we are subtracting something, then we would slide to the right. So if this was x minus 4, that means this thing slid to the right 4 places over here. If h is negative, so minus a negative would be like adding, that means it's sliding to the left. So if this was h minus -5, so x plus 5, we would slide to the left 5 places for the vertex. In a similar way, if k is positive, so what we're adding at the end, then we move upwards. And if it's negative, we go down. So if at the end of everything it said +2, instead of starting here, we would go up to here with our vertex, and then everything would stem off of that. So when k is positive, slide up. When k is negative, go down. When h is positive, so when we're subtracting something in here, we slide to the right. When h is negative, we slide to the left. If a is bigger than 1, everything gets narrower, it grows faster. If a is between 0 and 1, like a fraction, then it shrinks or it gets wider. And if a is negative, everything flips upside down. Now, once you get these rules down, all of the rest of them should be pretty much, should be very, very easy because they're all very similar. This next parent function we're going to look at is the square root function. So f of x equals the square root of x. It'll look like a sideways parabola, but only 1/2 of it. So we don't have this other part of the u coming out. We just have the top half. And it's kind of laid on its side. Now, one thing I want you to note, if yours looks like this one with the plus there, cross that out. It should be x minus h in here. This will look very, very similar to our quadratic one. There's an a in the front, an x minus h, and a plus k at the very end of everything, just like this. So these should not say x plus h, it should say x minus h. Okay? Now again, looking at our x-intercept, there can only be either 0 or 1 of them. There can never be 2 of them. So I'm going to draw, let's say we had a quadratic, or sorry, a square root function that looks something like this. So again, that's my kind of half of the parabola. Now, notice if I start it over here, so here's my vertex where everything's stemming off of, it does not, oops, I should start it above this. It'll continue to go up slowly, slowly, slowly up. It'll never touch this line. So there'd be 0 of them. Or it could come from underneath like this, and it'll come up and touch right here, slowly go up, and never touch again. So there'd only be 1. If I started way down here, it might not look like it's slowly going up, but it's slowly getting closer and closer and closer and closer until soon it'll finally touch way over here somewhere. So technically, there would still be an x-intercept. So there can really only be 0 or 1 x-intercept. For y-intercepts, again, depending on where it starts, there can only be 1 or 0 of them. If we start over here and move this way, there would never be a spot where we touch this y-axis. If we start on this side of the y-axis, though, and move this way, it has to touch that y-axis somewhere. So 0 or 1 of them. The reference points for our square root function are, again, the vertex. If you have it in this form, a times the square root of x minus h, and that's underneath the square root part, plus k, that's outside of the square root part, then your vertex would be at h and k again. So then, just like before, a is the stretch. So if a is bigger than 1, the curve narrows, or it grows. It's going to go faster, basically. If a is in between 0 and 1, then not the parabola, the curve, change that to curve, will widen or it'll shrink. Think of this more so as a shrink part. So by that, if we start here and a is bigger than 1, so let's say a is 2, that means it's going to be going faster than it normally was. It's going to grow up quicker. If a was 1/2, and it's going to be going slowly. It won't be going up as fast. It'll slowly go up, but not as quick as it used to be going. And again, if a is negative, everything gets flipped upside down, so we're going down this way. So it's very, very similar to the quadratic ones. The a is the stretch, and if it's negative, it flips upside down. Same thing with h. If h is positive, so again, we're subtracting, that means we slide everything to the right. This would just move somewhere over here, or this red one. We move it left or right, depending on if it's positive or negative. So if we're at x minus 1, this would slide over here. If we are at x plus 3, we would slide this over to negative 3. It's whatever's being subtracted, that's the x value of your vertex. And lastly, k, well, if k is positive, you go up. If it's negative, you go down. So if at the end it said plus 2, we'd have to move this up to 2. So right here is now at 2. If it said -4, we would bring this down to right here at a -4. So the stretch, the left and right slide, the up and down slide. Absolute value is going to be very, very similar. Again, I don't know what happened on the notes. These should not say x plus h, it should say x minus h. Otherwise, once we fix that, all of these will be very, very similar to everything else. X-intercept, there can be 0, 1, or 2 of them. This is true, again. It's pretty much just like the parabola. There can be, I'm going to draw this one in green. In fact, I'm going to draw it right over the top of our original one. Then we'll slide things from there. Right now, this vertex is just touching this line. So there is one x-intercept. If I started it up here, it would never touch this line, so there'd be 0. If I have it below, notice it touches here and here. So there are 2 x-intercepts then. So 0, 1, or 2. There always has to be at least one y-intercept. It has to touch this line at least once. So you'd plug in 0 for x and then solve for y. There's only going to be exactly one time where this line will cross the y-axis. Reference points like before, it's that vertex. It's our hk. When we have it in this form, a times the absolute value goes in these bars, of x minus h, all of that plus k. H and k make your vertex, your starting point, kind of that corner piece of your v. One thing you might want to note, all absolute values make this V shape. That's going to be the shape of an absolute value graph. So again, like before, A is our stretch. If A is bigger than 1, it's going to be going up faster. So it looks something like this. It's moving upwards a lot quicker than it was before. If A is in between 0 and 1, oops, again, not the parabola, the V will be going out more slowly. It'll be a lot wider than it was before. And if A is negative, flip everything upside down. So it might look something like this, going downwards. Suppose this one should rotate and flip too. That would be if A was negative. Everything would be going downwards. Again, like before, if H is positive, so if we're subtracting something, we slide it to the right. If H is negative, so we're adding something up here, you slide it to the left. And if K is positive, go up. If K is negative, go down. The last one we're going to look at is called a cubic function. Notice it has an x to the power of 3, x cubed. Key features of this is that it makes an S curve. It almost looks like a parabola, but it kind of double swoops itself this way. Now we won't go too deep into these. We'll keep these pretty basic, but there are times when you can get cubic functions that look something like this. This is a pretty classic cubic function. Notice that it changes directions 3 times. It's going once, well, changes twice, but the directions are 3 different ways. It's going upwards this way, then back down, then back up again. So 3 different directions throughout it. That's what the 3 stands for. Okay, cubic, there's only 2, so once it's going up, once it's going down. Okay, it makes the parabola. But when it's a cubic, there are 3 that it can be doing. Now this one, this change of direction is so small that it almost looks like it gets flattened out and then continues to go on. That's why this one doesn't look as severe as this one. But all cubic functions do technically make this S curve. You can kind of see this S curve going on here. So, like before, we're going to look over the x-intercepts. There can be 1, 2, or 3 of them. This one, no matter where you start at, there has to be at least 1 x-intercept. Now there can be 2. There can be 2 spots where you cross the x-axis. And again, that might look something like this. Cross once there, once right there, and then go back up and away. So that it is possible to have 2 of them. It is even possible to have 3. 1, 2, 3, and continuing on. So there can be 1, 2, or 3 of our x-intercepts. For y-intercepts, there can only ever be 1, and you find it by plugging in 0 for x and then solving for y. Reference point, same as before. As long as this is minus h and plus k right here, your vertex is going to be hk. So for our parent function, the vertex is right here at 0, 0. And again, in fact, that's true for all of our parent functions. The vertex is always at 0, 0. A becomes our stretch. If a is greater than 1, the curve narrows or it grows. So it might look something like this then. If it's bigger than 1, it's going to go up faster, and as it turns, it's going to go down faster. That's if a is bigger than 1. If a is smaller than 1, so again, like it makes a fraction, it's going to make it kind of widen out a little bit. So it's not growing quite as fast. That would make it the curve kind of grow or shrink. And again, if a is positive or is negative, everything flips upside down. So it would look something like this then instead. Everything just flips over this x-axis. H, like before, will move left and right. Our vertex, again, that kind of turnaround point, depending on if h is positive or negative, and k moves everything up and down. Now let's look at some of these examples. If this is our function that we're looking at, what is our parent function? Now what are we looking for? This piece right here, because it has that 2, our parent function is the quadratic. It's the x squared. Now what is different about this from x squared? Well, in this one, our a value, the thing out front, a equals 1, and it's positive. So there's no flip, and it doesn't stretch, because it's not bigger than 1, it's not smaller than 1. Our h value equals 2, because we are subtracting 2 from x. And our k value, this piece at the end, it's like a plus 0 here. So k is 0. This didn't change it, this didn't change it, this changed it. If our h value is 2, that means we moved 2 units to the right. So these two graphs are going to look exactly like each other, only this one shifted 2 units to the right. Same thing, we're going to look at this one. F of x equals the square root of x plus 3. What is the parent function? Well, it's our square root function, square root of x. Now what was different about this from this one? Our a value is 1. It's positive, so it didn't flip. It's not bigger than 1 or smaller than 1, so it didn't get wide or narrow. Our h value, remember h would go underneath the square root with x. H is 0, meaning it didn't slide left or right. But our k value, the thing at the very end, is a plus 3, positive 3, which means we moved 3 units up. Take this function and just slide it up 3 places. That would be what your new function looks like. One more time, this was our function. F of x equals 6 times the square root of x. What's our parent function? The absolute value piece. So this one's going to make a v. What was different about it? Well, I'm only going to show you the piece that is true. Our a value is 6. Notice there's no h in here. There's no k at the end. Just that there's an a value of 6. So what does that mean in terms of our v shape? Well, it's stretched six times, you can say either bigger or faster. I'm going to use bigger. So if we needed to graph this out, our normal one, the original one, I'm going to do this in red, looks something like this. Goes off that way and goes off that way. it goes up 1 over 1, up 1 over 1, up 1 over 1. Left 1, up 1, left 1, up 1, left 1, up 1. That's the kind of classic absolute value V. Now for our shape, the V that we're going to draw, we're going to go up or over 1 and then up 6. 1, 2, 3, 4, 5, 6. So we're growing 6 times as fast as we used to be. So our V would look something like this. And I'm going to change it to purple. Start from here and it goes up like that. So notice, they still look pretty similar. They still have that V shape. This one is just 6 times faster. So it makes it kind of narrow in this case, because it's growing way faster than the original red one was. How about for this one? X cubed plus 8. What was our original parent function? Well, it was the cubic function, the x cubed. What was the transformation? We went up 8, because this is plus 8 at the end. Notice that the plus 8 is not within the cubic part. It's not inside the parentheses with x. Doesn't look anything like that. It's on the outside, so it means we're going up 8. So if the normal curve starts here, up 1 over 1, down 1 over 1, and then makes kind of this S curve, something like this. This would be our normal cubic function. Well, I'm going to take these, make them red here. This then would be our new one. We just take it and slide it up 1, 2, 3, 4, 5, 6, 7, 8 places. I took this vertex right here and just slid it up 8. Now, this is what our new transformed graph would look like. Example 5 says, write the equation of each graph that was given. So this one makes a V shape, so we know it's going to have an absolute value piece. I'm going to say y instead of f of x. You can say f of x or y, it doesn't matter. Now this one is going upwards like it should be, so it's not negative, it's a positive amount. From its vertex, it's going up 1 over 1, up 1 over 1, up 1 over 1. So the a value is 1. So we really don't even need to write that in there, but I'm going to anyway. Now, from our original spot here at 0, 0, we slid to the right 2, and we slid up 1, 2, 3. So inside the absolute value would be x minus 3, minus our h value, and then plus our k value. Oops, this should actually be minus 2, sorry. We only went over 2, and then we went up 3. So we don't really need this part. Our equation would just be y equals absolute value of x minus 2, and then plus 3. Plus 3 goes up 3, the minus 2 goes right 2. Same thing. Here we have that S curve, so we know it's going to be something cubed. Y equals something cubed. Now from our vertex right here, we went up 1 over 1. Same thing, over 1 and down 1. So our a value is 1, and it wasn't flipped, it's not negative here. So this time I'm just going to not write anything for a. Our vertex did not go up any. So it's like a plus 0 at the end. We did not go up any, so our k value is 0. And inside here, x minus, how far over did we go to the right? We went 3, so minus 3. So in the end, we don't really need that. We can just say y equals x minus 3 cubed, because it slides it over. Example 6, looking at the parent equation and description, write the equation. So for part A, it says, my parent graph is the square root function. So it's going to look something like this. Y equals square root of, with an x in here. Now there could be something out here for A, something in here for H, something out here for K. So let's look at what each thing says. I've been shrunk by a factor of 6. So shrunk means you're going down So it's like a fraction in between 0 and 1. So by a factor of 6 means 1/6. It's 1/6 of the size that it was before. I've been shifted up 3 units. So that's our k value. Plus, oops, about to write k, plus 3 in the end. It doesn't say anything about left or right, so we kind of ignore that. So it would just be y equals 1/6 times the square root of x, and outside of the square root plus 3. That would be our equation then. For this one, it says my graph is the quadratic function. So y equals, this one being quadratic, will have a squared x in here. I've been reflected across the x-axis. When it reflects or flips over, we know that our a value has to be negative. My vertex has been moved 2 spaces upwards, so plus 2. Now they didn't say anything else, so we can consider this -1, or we can just call it negative. They didn't put anything here, so it's just going to be x squared. So we can call this y equals negative x squared plus 2. If you want, you can call this a -1. You don't have to put the 1 in there, but it does have to have negative because it was flipped over the x-axis. There shouldn't be anything in here with the x, just x is being squared, and then plus 2 at the end. And that'll cover it for our last video.